right, so now we're talking limits at infinity. So yesterday kind of sounded similar, right? We said, or yesterday, 2 days ago, limits to infinity, right? Now doing limits at infinity. They kind of sound similar, but they're different ideas. Okay, so today, all of the limits are going to be approaching either one of two places, positive infinity or negative infinity. So where is positive infinity or negative infinity? Where are those on the graph? Where are those on the graph? Like positive infinity and negative infinity for x. Like on this graph you see in front of you, where are those values? Where's positive infinity? Very far right we can go until we can go any further. Yeah. So if I were to follow the graph here and kept going and going and going until I can't go any further, that's where positive infinity would be, right? In theory, it exists, but it doesn't really exist because infinity is not a number. Infinity is an idea. Okay. Same thing with negative infinity. Where would I be if I went this way forever and ever and ever and ever and ever and ever? Well, we can actually graph that because it's not a real place. Infinity is an idea. Okay. I can't add infinity plus infinity, right? My son just developed the idea of infinity. So he's like, well, isn't infinity plus one bigger than infinity? I was like, no, it doesn't exist, right? Infinity's not a place. It's somewhere you can head towards, but you're not actually get there. Okay. So you can't add anything to infinity, right? That's what infinity is. It's an okay. So here we go. I did a couple here. I did a couple tables to show you what we're talking about, right? So here's the function here. In other words, limits at infinity are talking about its end behavior. End behavior. End meaning the end of the road. Behavior, how it is. So how is it acting at positive infinity? How is it acting at negative infinity? That's what end behaves. Okay. Okay. As I go to positive infinity, plugged in numbers. I did this most. I put 1 into the equal, and I got 1.4. Plugged in 100, got 2.7. Got 1,000, got 1,000, got 100,000, million. I plugged in. Eventually, I got so close to 3. It's not even 3, but my calculator. What happened is the calculator said it's 2.9. They don't want to write all those numbers, so they said it's 3. They just said it's just okay, but it's not 3. It's like 2.997 or 8 or whatever. Okay, some calculators will do that. They'll say, you know what? It's so many decimals. I don't want to write it, so round. Okay, so that's what it did. And then I did the way. I plugged in negative numbers, way to negative a million, and it did the same thing, right? What the table is doing is showing you the limit as x approaches infinity. Well, since we have the table, it's 3. We know this is 3, and this is also 3. So it's not that bad. But here's the catch. I used the calculator to come up with tables. I didn't plug it in. I plug in a million in my head or on paper. I use a calculator. These are on calculator questions. So how do we do it if we don't use a calculator? That we're going to show you today. That's what I'll show you today. Okay. So I wanted to show you the idea. Okay. I just want to show you what the idea of sorry, give me 1 second. Of what it means. Okay. What this idea of approaching infinity and approaching negative infinity. Okay. Okay. So let's go to the next one. Okay. So at infinity, what's created when we approach infinity or negative infinity, what's created sometimes is a word you've seen before, asymptote. But it's not a vertical asymptote. It's a horizontal asymptote. Okay. So what was a vertical asymptote? Someone remind me what a vertical asymptote, what's the definition of a vertical asymptote? Your best definition. I don't need the textbook definition, but what's the best definition that you can come up with of a asymptote? Yep. Perfect. That's it. It's an imaginary line that the graph can't cross, right? So is for vertical asymptotes, which way is that imaginary line? Right? Vertical, right? A vertical asymptote, right? This is the same exact thing, except now the line is horizontal. So instead of being able to go, it can't go left and right, right? Now it can't go up or down. It's stopped. So let's go back to that. Look at that first graph. There's a horizontal asymptote there, right? There's a line, an imaginary line that it can't cross. This is it right here. It's the same as the limit as x approaches infinity. It's the same as the limit. Okay? It's that imaginary line we'll never cross. That's why I kind of got mad at my calculator here at Desmos, because this is not actually 3. These numbers aren't actually 3. It's never going to touch 3, right? It's going to be 2.9999, but Desmos got lazy and said, I'm not going to write that. We're just going to write 3. So these numbers aren't actually 3. They're 2.9999, go on forever and ever and ever, right? So that's the horizontal asymptote. That's what we're looking at today. Horizontal asymptotes. Okay? Last 2 days we talked about vertical asymptotes. Today we're talking about horizontal. So where are horizontal asymptotes? Where are horizontal asymptotes? This is in words. I have a table. On the next page, I have a table, which probably be easier for you to use. But this is in words where the horizontal asymptotes are. Okay, so if we have a function that's approaching positive or negative infinity, okay? If the degree of p is greater than the degree of q, so if the top degree, so remind me again, what is a degree? When I talk about polynomials, what is a degree? Does anyone know what a degree is when I say that word? Yes, Risky? Perfect. The largest exponent. Okay, so when you see the word degree, that means largest power or exponent. And I spelled exponent wrong. Okay. That's what that word degree means. Okay. So if the degree of p is greater than the degree of q, then the limit is positive or negative infinity, depending on the signs of the leading coefficient. We call that top heavy. We call that top heavy. If the degree on top is bigger than the degree on bottom, it's top heavy. And your answer is either going to be positive infinity or negative infinity. Okay? The next one says, if the degree of p and q are the same, the limit is the leading coefficient of p divided by the leading coefficient of q. So that's if they're equally balanced. We call that equally balanced. That means the limit on top, or sorry, not the limit, the degree on top is the same as the degree on bottom. The last one is the easiest one. If it's bottom heavy, if the degree of p is less than q, it's bottom heavy. If that's the case, the limit is always going to be 0. Okay. Okay, so next on the back, I have a table that's probably make a little more sense with some examples on it. I'll give you some examples. Okay, so once you're done with this, if you go to the back, I'll show you the table. It's the same thing, but in a table form instead of words. Okay. Okay. So just like we talked about, degree of numerator is larger. That's top heavy. Degree of denominator is larger, bottom heavy. Degrees are the same, equally balanced. Okay? So if it's top heavy, we just read that if it's top heavy, the limit is either going to be positive infinity or negative infinity, depending on the signs of the leading coefficient. Okay? So where are the asymptotes going to be then? The asymptotes, there will be none. Okay? Because if it's positive infinity or negative infinity, it's not going to stop. It's going to keep going up and up and up, or down, 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 down. It's not going to stop. So there will be no horizontal asymptotes. There's no horizontal asymptote. The example I'm going to give you: y equals x cubed plus 2x over 2x squared minus 3. What's the degree on the numerator? What's the numerator degree? 3. What's the denominator degree? 2. The top is higher than the bottom. The top degree is higher than the bottom. It's top heavy. So if that's the case, we would get a limit that's either positive or negative infinity, and we would have no horizontal asymptote. No horizontal asymptote. Okay. What about if it's bottom heavy? If it's bottom heavy, we learn that the limit is always 0. The limit is always 0, right? I should have underlined or highlighted these. Positive and negative infinity, depending on the signs. And limit is 0. Okay, so we learned that the limit is 0. So guess what? The horizontal asymptote will always be at y equals 0 as well. Bottom heavy. Bottom heavies are the easiest. Limit 0, horizontal asymptotes are at 0. Let me give you an example of bottom heavy. Here's an example of bottom heavy. X squared minus 3 on top. So we have on top the power, or the degree is 2. On bottom the degree is 3. It's bottom heavy. That the highest power is 2 on top. The highest power on bottom is 3. Bottom heavy. So that means where is the horizontal asymptote? It's going to be at y equals 0. Okay. The last one is equally balanced. Equally balanced. Okay, so equally balanced, it said is, let's see, the limit is going to be the leading coefficient of P divided by the leading coefficient of Q. That's not as hard as it sounds. They make it sound a little difficult. It's not. It's the ratio of leading coefficients. Ratio of leading coefficients. So a couple buzzwords there. What's a ratio? How do we write? In other words, how do we write ratios? In this class or in high school math, how do we write ratios? Or what is a ratio? Let's start there. What is a ratio? Can you give me an example of a ratio? I bet you can. You just don't know it. So a ratio, back in junior high or high school or elementary school, you did ratios like this, right? So there's 5 pieces of pizza. I have 3 of them. That's how you started. And then you said, okay, no, we're not going to write it like that. So instead, how did we write it? As a fraction. I have 3 pieces of pizza out of 5 total, right? And then sometimes you can change it to a decimal. Sometimes you can change it to a percent. Those are ratios. Those are all ratios. 3:5, 3/5, 3.6, 60%. Those are all ratios. Well, in this class, we write ratios like fractions. So it's a fraction. Okay. What's leading coefficients? What is a coefficient first? What is a coefficient? Arthur? A number that comes before a variable. Yep. So let's do an example here. So what's the coefficient of x cubed? 1. What's the coefficient of 2x? 2. Okay. So we know what a coefficient is. Leading coefficient. Leading coefficient. Okay. So we have 2 coefficients up here. We have 1, right? And I have 2 here. Which one is the leading coefficient and why? 1 or 2? It's actually 1. Why? Well, it comes first. Well, can I change that though? Can I write it like this instead? I don't like it like that. Can I write it like this? Still the same thing, right? Then it becomes 2. So which one is it, right? So there's another reason. Not because it comes first, but because what? Yep. Because it has the degree. Yeah, it has the degree. Whichever number has the degree is the leading coefficient. So this is the leading coefficient here is 1. The leading coefficient here would be 2. So the ratio of the leading coefficients is 1/2. Okay. That's what I mean by leading ratio of leading coefficients. Okay, so let me give you an example. So 3 minus x squared over 5 squared, 5x squared plus 2x. So what is the degree on top? 2. What is the degree on bottom? 2. Okay, equally balanced. So what would be the leading coefficient on top? -1, good. So it's going to be -1. Oops. What's the leading coefficient on bottom? 5. So a ratio of those guys would be y equals -1/5. Okay. All right. Okay, so here's the thing. Sometimes they are not going to, sometimes they're going to be a little confusing because you're going to look at something, you're like, is that top heavy? Is that bottom heavy? Is that equally balanced? I don't know. They're not going to be as clear as day. Look at B. Is that top heavy, bottom heavy, or equally balanced? I don't know, right? So I have a little cheat sheet for you guys. This little growth rate chart. The top grows the fastest. So factorial, but you don't have, in AB, you don't have factorials. So don't worry about factorials. What is a factorial? Don't worry about it. You won't see factorials. You'll know it if you see it. Like if you'll have 6 exclamation point, that's a factorial. Okay, we don't have that in AB, so you don't have to worry about it. There you go. That's what 6, so 6 factorial is the same as 6 times 5 times 4 times 3 times 2 times 1. You won't see anything like that. So the thing in this class that grows the fastest are exponentials. What is an exponential? How do I know I'm looking at an exponential function? What gives it away? So not the exponent, because I can do this. That's not an exponential, that's a quadratic. Yeah, there you go. If x is the exponent, x has to be the exponent. X is exponent. X is the exponent. Polynomial, which you guys are used to seeing. Quadratics, cubics, x to the third, x to the fourth, x to the fifth, x to the 12th. That's what you're used to seeing. Okay, polynomials are what you're used to seeing. The next one is logs. Logs. Anything with a log or a natural log grows slower than exponents, exponentials, or polynomials. After that, sine and cosine. Why do sine and cosine almost at the bottom? Why are sine and cosine almost at the bottom? What do their functions do? What do sine and cosine do? They oscillate, yeah. They go like this. Up, down, up, down, up, down. And where does sine and cosine top out at? Where does the top of sine at? What's the biggest value I could ever have for sine? Sine of anything. Look at your chart. What's the biggest number you see? 1. What's the lowest number sine can be? -1. So it doesn't grow very fast because it tops out at 1, right? And -1 is the lowest it can go, right? Same thing with cosine. Cosine's the same thing. Tops out at 1, bottoms out at -1. So it does go up and it does go down, but it doesn't go up past 1 or down past -1. That's why it's down on the list. Okay? Constants don't go up at all. They just stay constant. That's why they're the lowest, because they don't go up at all, right? So that's why. So anything exponential is going to be growing faster. So what do I mean by growing faster? Well, anything exponential is going to be the largest. Okay. All right, so let's look at number 1. Let's look at 1A. Let's start doing some problems. So as the limit as x approaches infinity for this guy here. Okay, so the only place to plug in any number would be here, right? That's the only place to plug in. 5 is just 5. I can't plug in anything for 5. So this is what I'm going to do. I'm going to separate this. I'm going to rewrite it. The limit as x approaches infinity for 5 minus the limit as x approaches infinity for 2 over x squared. The reason I did that was because it's easier to do it in smaller chunks. If you have anything that has a plus or a minus, I suggest doing that because it makes it easier. So let's start here. What's the limit as x approaches infinity for 5? 5. It's always just going to be 5. There's nowhere to plug in anything. It's 5, right? If I had the graph y equals 5, and I followed that graph right as far as I could, guess what the y value would be? 5. It would always be 5, right? So the limit is going to be at 5. So this guy right here is 5. Now let's go over here. Oh, wait, this guy, I have somewhere to plug it in, right? I can plug it in on the bottom. I can plug in a number on the bottom. Well, you can't plug in a number if I don't know the number. So what are we going to do instead? Why would it equal 0? You're right. Why would it equal 0 though? No. Why does it equal to 0? It is. That's the answer. The answer is 0 to this. But why? 2 words. I think I just heard it. Where does it fit on this list? Bottom heavy. It's bottom heavy. The degree on the bottom is 2. What's the degree on top? 0. It doesn't have one. It doesn't have an x. If it had an x, that would be 1, right? But it doesn't have one. That's why it's nothing. So it's bottom heavy. So if it's bottom heavy, the answer is going to be 0. So 5 minus 0 is 5. Okay. Bottom heavy. BH means bottom heavy. Okay. Now let's go to B, the one we looked at about 5 minutes ago. Okay. So 3 is just 3, right? 3 is just 3. The bottom, what type of function is the bottom? Exponential, right? What do we know about exponentials? They grow the fastest of what we're going to see. They grow the fastest, right? So the bottom, as I plug in numbers for x, 1, 2, 100, 1,000,000, 10 million, as I plug in there, 3 is going to stay 3. The bottom is going to become bigger and bigger and bigger and bigger and bigger and bigger. What happens to a fraction when the bottom becomes bigger and the top just stays the same? It gets smaller. It gets closer and closer to 0. That's why it's bottom heavy. This guy is bottom heavy. Okay? So if it's bottom heavy, the limit is going to be 0. This guy is bottom heavy as well. Okay? All right. Let's look at C. So now we have a choice. Top heavy, bottom heavy, equally distributed. I'll give you a hint. It's not equally distributed. Which one is it going to be? Top heavy, bottom heavy, equally distributed. Well, if you don't know, look at your chart. Which one's growing the fastest, the top or the bottom? If it's higher on the list, it grows faster. If it's lower on the list, it grows slower. So we have one that's a trig function, right? What is x? Where does x fall on this list? Is it a exponential, polynomial, log? Is it a trig, or is it a constant? Not a constant. It's a variable. X is a variable, so it's not a constant. It's a polynomial. It's a polynomial. It's a polynomial. So since it's a polynomial, it grows faster than a trig function. So let's go back. Is it top heavy or is it bottom heavy? Which is growing faster? The bottom. So if the bottom is growing faster, it's bottom heavy. Yep. Bottom heavy, 0. Okay. Letter D. Top heavy. I agree. It is top heavy, right? It is top heavy because you got a 2 here, and that's just a 1 because that's the highest degree, right? Top heavy. What's the difference here between this one and the ones we have seen besides top heavy? So top heavy, yeah, top heavy doesn't have horizontal asymptote, right? So if they asked us, if the question was, what's the horizontal asymptote, we would put none. But the question's not asking us that. It's asking us for the limit, right? So let me go back. Let me ask again. What's the difference between this one and the three previous that we saw, besides bottom heavy? Besides this one's being top heavy, what's another difference? Take a look at it. Take a look at this one. Take a look at the other three we've just done. What's the difference? Hmm? No, no, that's not the difference. We're going the opposite way, right? We're going the opposite way. So now we're not talking about positive numbers. We're talking about negative numbers. That matters. Okay, that matters. Okay, so what did they say the limit's going to be if it's top heavy? What did the note say? Positive or negative infinity, right? Positive or negative infinity. That's going to be our answer. Which one, though? That's the thing we got to figure out. Is it going to be positive infinity or negative infinity? It's going to be one or the other. So this is how you figure it out. If I was to plug in, because this means plug in extremely big negatives, right? -1, -2, -3, -100, -1,000,000, -100,000,000, -1 billion, right? So let's say I'm plugging in negative, those big negatives. What would I get on top? Would I get a positive answer or a negative answer? Positive, right? Why positive? You're right. Why positive if I plugged it in on top? You square, right? You'd square it. And then you multiply it times 3, right? This guy would be negative, but this guy wouldn't even compare to this guy. So this guy would rule, right? So I'd get a positive on top. What about on bottom? Would I get a positive or negative on top if I were to plug in one of those huge negatives? I would get a negative, right? I get a negative on bottom because you have that negative number -1, bigger negative, right? So if I divide those, what type of answer would I get? Negative answer, right? So that's why this guy is equal to negative infinity, not positive infinity. Okay, because of that. Okay. There's not a lot of work to do on these guys. On these, there's not a lot of work. Kind of like the one we did, the practice problem, the homework problem we did earlier. It wasn't a lot of work. It was just kind of a lot of thinking. That's what this is. Okay. It's nice because there's not a lot of work to show, but it's just between the ears, knowing what you know, using your notes to kind of go over it. Okay. So let's look at the next one. E. What's the difference between E and the ones we've seen previously? Square root, right? It's got a root. Absolutely. We haven't seen one with a root. Okay, let's treat it the same. What is the degree for the top? 1. What is the degree for the bottom? It's not going to be 2. It's actually going to be 1. Why would it be 1? Exactly, because anything I plug in, I'm squaring, right? But then what do I have to do after I add 4? Take the square root, right? So that really, they're canceling each other out. So the degree here is not really 1, or sorry, it's not really 2, it's actually 1. Okay, so really you have x to the first over x to the first. The 4 I don't care about. I don't care about the 4 because all I care about is the leading coefficients. That's all I care about, leading coefficients. So now they're equally distributed, right? So what did it say with the limit? How do I find the limit if it's equally distributed? Or the asymptote, horizontal asymptote? A ratio of the leading coefficients. Okay, so I have the leading coefficients over here. What's the leading coefficient of the first one? 1. What's the leading coefficient of the second one? 1. 1 divided by 1 is 1. Okay. All right, let's look at it. Try F on your own. I want you to try it. Try it. I'll give you a few minutes. Come up with what you can. It's gonna be a lot of thinking because there's a couple things that you got to take into account. Okay, try it. I'll give you a minute or two, and this is the last thing we'll do. Last problem we'll do. Okay, so now there's no division, or sorry, there's no roots or anything like that, right? So we can look at top heavy, bottom heavy, right? They're both polynomials, right? They're both top and bottom are both polynomials, right? So what's the degree on top? 3. I agree. What's the degree on bottom? 3. I agree. I agree. Sorry. Those are the guys I care about. I don't care about anything other than that. So I'm going to focus on these two guys right here. The 7 and the 1 are meaningless to me in terms of this problem. Okay? So I'm going to rewrite it. I have negative 3x cubed, and I have positive 2x cubed. What's the limit going to be? If this said right here, positive infinity, I'd go 100% with that. That could still be the answer, but I'm not sure. I have to take into account that, hey, I'm going to be plugging in negative numbers. So I have to check to see if it's going to be positive or negative. So let's look at the top. If I were to plug in a big negative, would I get a negative number or a positive number up here? Because this guy would give me a negative, right? And then this guy would give me, multiply it, it would give me a positive, right? Good, I like that. So positive. What about the bottom? What if I plug in a really big negative number? Would it give me a positive or a negative answer? Right? So my answer has got to be negative. My answer does have to be negative, right? So it would be, in fact, negative 3 over 2 because of that. Okay? If that were a positive on the bottom, it would be positive 3 over 2. Okay? I just wanted to double check that I would still get a negative and a positive because signs count. Okay? All right, guys. Okay, we'll pick up where we left off tomorrow. So the homework assignment, work on that if you haven't. The one I assigned yesterday, if you haven't finished it, work on that. It's not due till tomorrow, but still,